Thank you for the introduction. I'm very happy to be here today. I'll be talking about modeling CO2 storage in geological formations. And since we are a very diverse group of researchers and people, I'll start very broadly and slowly work my way to the research that I'm conducting. So what is geological storage, very, very broadly? So basically it's part of a bigger technology called CCS, carbon capture and storage. The capture part means that you separate the CO2 from other components in your emission source. So your emission source can be a power plant, can be some factory. Once you've captured the CO2, it's usually compressed to a supercritical state, so it's easily transported in pipes to a location where you're going to inject the CO2 to a geological formation underground. Now the different formations that you can inject CO2 in, well, there's a list here of some of the possibilities. The most popular is deep saline aquifers. So these are aquifers that have water that we're not using, we're not drinking, they're salty. And other possibilities are unminable coal seams, depleted oil and gas reservoirs. Another popular option, which is also financially viable, is enhanced oil recovery injection, where the CO2 is injected into an oil field, and then it enhances the production of the oil. And this can be done in combination with storage, so storing the CO2. Altogether, I'll talk about this more, but altogether this is feasible technology that's being conducted as we speak. And it's estimated that there are thousands of gigatons for storage space for CO2. So thousands of gigatons of CO2 can be stored underground. And for comparison, we're emitting about 30 gigatons annually these days at least. So a bit of the history of CO2 storage is the timeline. So you can say it started in the early 70s with enhanced oil recovery by CO2 injection, although the goal here was not to store CO2. So basically it was the opposite, to get the CO2 out, as much of it out so you can re-inject it. But the idea, you can say, started here. To being an actual storage for lowering emissions and mitigating climate change, that began early in the 1990s, and then academic research started. 1996 was the first actual project, the Sleipner project. It's still running today. It has sequestered approximately 16 megatons of CO2, and this is in Norway. And the reason this started was very simple. There was a Norwegian carbon tax. So this made it financially worthwhile for Statoil to inject the CO2 underground. This is CO2 that they separated from natural gas that they produced. So instead of just emitting it, they injected it underground to save the tax. In 2000, another large project, the Weyburn project in Canada, where the CO2 is injected for EOR. 2003, the budget, so this is a process whereby the budget for CO2, for CCS, has increased. And this is, of course, very important to promote the technology, the budget. So it rose from like $1 million in '98 to $54 million in 2003. Another important point, in 2005, the IPCC special report focused on CCS, basically established this as a feasible technology and also contributed to pushing this technology forward. 2015, another project in Canada, the Quest project, where the CO2 is stored in a saline aquifer. This is expected to have about 27 megatons ultimately as the project finishes. In 2017, the last CCS report states 21 large-scale projects operating. This is kind of a figure to show the many projects that are currently operating in blue, future in green. Now this is not updated, this is from the 2015 CCS report. You have here the Sleipner project, the Quest, Great Plains is the Weyburn, so we talked about these three in the previous slide. You have here, the circles correspond to the size of the project. The really big circles are more capture projects, not exactly storage. These are capture projects in Texas where they capture the CO2 and then pipe it to oil fields for enhanced oil recovery. But again, enhanced oil recovery does not necessarily mean you're optimizing storage. It could just be coming out as well, CO2 as you inject it. But the green ones actually, the Gorgon project in Australia is already operational very recently. It's the largest project currently operating of CO2 storage. It's injected into a deep saline aquifer as well. So quite a few, quite a few operating projects, however, not as many as could have been, so it's still not game-changing technology as was once thought it would be. And so let's talk about the issues and questions. So I would say the last point here is probably the main issue of why this hasn't bloomed to be the very promising technology that we once thought. Financial and political constraints. Of course, if you implement some tax, if you regulate, and you make it financially worthwhile, this will happen much, much more. But this is not the focus of my talk. I'm dealing more with the physics. So what are the questions that do arise when you approach a new project, when you look at a new reservoir? You have to ask yourself, what is the storage capacity of that reservoir? How secure is the storage? So how long will the CO2 remain in that reservoir? You have to think about leakage. So the CO2 rises to the top of the reservoir because it's lighter than the oil, lighter than the water, or oil if there's oil there. And ultimately, it all accumulates at the cap rock. And then if you have cracks, you could have leakage. If you have wells that are not shut down correctly, they could leak through old wells. And these are things that need to be considered. And you need monitoring during the operation. And all of these three major questions are directly related to flow modeling, which is my research field. So you have to implement and build flow models to estimate where the CO2 will spread, what the pressures are going to be, and assess the risks for leakage and so forth. So flow modeling, very basically, you identify the region where you are injecting the CO2, and you need to make a physical model by solving the equations. So the physical model, you have to construct it, you have to know the boundary conditions, so basically what the reservoir looks like. You have to characterize the porous rock, parameters like permeability, relative permeability, capillary pressure, dissolution rates, many, many factors. And then you basically solve these models, usually numerically, and you get something like this, so the CO2, how it spreads. A lot of time it will rise to the top and accumulate around the cap rock, but not always. So here's an example. This is the Sleipner data. So Sleipner project, they release a lot of the data, which is very nice, and it's very helpful to the scientific community. So you see here seismic 4D images. It shows you how in time the CO2 plume expanded. And this is just the top layer, so we don't see the depth. This is the top layer close to the cap rock. And below you can see two models that try to kind of estimate the same development as the seismic images show. And what you can see is both, well, you see the black lines, they show the extent of the plume from the seismic images. Here it's the white lines, I don't know if you can see them. But what you can see is they're not very good. So here there's a significant overestimation, here there's some significant underestimation. This figure kind of summarizes 6 different flow models, and this is the gap area. So this is just the underestimated gap area. It's not even the whole error. You can see significant gap areas between, what is this, like 15% to 35, 40%. So the flow models do not work as well as we expected. What are the challenges of flow modeling, and why is this so difficult? Basically because four main points. It's a there are multiple complex physical processes going on here. This is multi-phase flow in porous media with multiple components. You have dissolution of CO2 into water. You have capillary pressures effects. You have heterogeneity of the rocks. Geochemical reactions between the CO2 and the rocks. And all this makes for very complex nonlinear equations to solve. The problem is multi-scale. What does that mean? The multi-scale nature of it comes from the heterogeneity of the rocks. So if you look at a rock at a very small centimeter scale, you may see some sandstone with shale lenses. But when you go up in scale, you look at it at meter scale, it may look completely different, layered. So it's still composed of those centimeters, but it gets a different large-scale characteristic in terms of the permeability. This is the multi-scale problem, and it calls for upscaling and other analyses. Lack of data, we don't know what's going on underground. We have some samples, we have well tests and seismic data, but the lack of data is very important. We need to make the problem stochastic, meaning we generate many realizations, many options for how the reservoir looks. For every option, we need to solve the flow model. So this makes it very complex, and all these together make it computationally very difficult. So you combine all the things together, and you get a lot of simulation time, basically, to solve the problem on top of everything. So the approach that me and my research team take is to try to identify and learn about the basic fundamental mechanisms, and then we can distinguish whether it's a mechanism that is important for our flow problem or whether we can neglect it. And that will, of course, simplify. We also build simplified models of the flow. So a very general overview of the trapping mechanisms. Structural trapping, so this is how CO2 stays underground, basically. It stays either by structural trapping, where it just goes to the cap rock and stays there because of a physical impermeable rock. Residual trapping happens when the CO2 is stuck in between the pores of the porous medium. So it can remain inside, not at the top, but it will be trapped because of the porous medium nature, capillary effects. And this takes a larger time to happen, and even larger time takes for the dissolution. So the CO2 dissolves in the water, becomes just like the water on your table, basically, the fuzzy water. And this is a safer storage option. And then the safest option, but the largest time scale, is mineral trapping. And this was mentioned in a couple of talks earlier about where you can store in basalt rocks. So this is the safest sort of type of trapping. There's a geochemical reaction between the CO2 and the rock. So, as I said, we look at the mechanisms. We're going to focus on the residual trapping mechanism. And we conducted a numerical experiment here. So think of a block of porous media, and you inject CO2 at the bottom. So this is what you're seeing here. This is the CO2 saturation. And then you stop injecting, and you just let gravity do the work, right? So what happens if there's no capillary effect? CO2 is lighter than the water, it just goes to the top, and you get all the CO2 at the top. But with capillary effects, you start getting these trappings, so CO2 remains in the lower parts of the rock. If there's small capillary effects, you just get less trapping, isolated blocks. If there's large capillary effects, you get these bigger structures of trapping. And by capillary effects, for those of you who are not familiar, I mean the surface tension, right, that happens between two fluids and a rock. And so we wanted to understand a little bit more in detail what's happening here. So we looked at the capillary pressure, which is, again, the surface tension effect. And we also looked at the saturation. So you see for the top part, there's one type of trapping mechanism. Here, you have CO2 everywhere. And the capillary pressure is varying hydrostatically, so it's nice and smooth. And so the reason the CO2 doesn't continue to go up is because of this equilibrium between capillary pressures. So it basically has an equal capillary pressure to the block next to it, and it doesn't continue to rise. This is one type of trapping mechanism. The second one, if we look at this block here, this block is surrounded by water. So the water has no surface tension in it, no capillary pressure really. It has an entry pressure, capillary entry pressure. And this is the block with the saturation. You can see it has a much lower capillary pressure than the surrounding blocks. It's hard to see this in the middle. So the idea here is that if you have CO2 surrounded completely by water, the trapping mechanism is an capillary entry pressure mechanism. The CO2 will not continue to rise upwards because of entry pressure that's larger than the capillary pressure of the block with the CO2. And then we went on in this project to basically derive a simplified model, but I will not go into the details of that. And then a second project, we're looking at the injection stage. So before we saw just gravity. It was gravity and capillary effects. But now we're looking at gravity, capillary, and viscous effects when you have injection. Is this going to play itself? Or? This is... So we inject here at this point the CO2, and you can see it spreading. Now, if there's no capillary effects, it spreads really nice and smoothly, but the capillary effects cause these preferential flow paths and these chunks of CO2. And you can also see gravity effects, right? There's more CO2 on top than the bottom. And the interesting thing is that the trapping here, the entry pressure trapping, this mechanism that I talked about in the previous slide, it actually happens on the water, not on the CO2. So here you get chunks of water surrounded by CO2. I'll show the second one. Here it's even more pronounced, the impact of the capillary pressure effect. You get these blobs of the CO2, and you get trapped regions of water. So the mechanism here is trapped water. So you get water surrounded by CO2, and the capillary entry pressure of the water is large compared to the capillary pressure around the water. So the CO2 does not penetrate these blobs, again, because of the entry pressure mechanism. And that's what we're seeing here. These ones are lower, these ones are higher. This is the entry pressure, the ones inside the water region. Then the adjacent capillary pressure here, so the CO2 doesn't enter. So to summarize, geological storage is feasible technology that can help reduce CO2 emissions. The modeling is essential for this. However, it's also challenging. To overcome, in my research group, we study fundamental processes and develop simplified models. And then I talked about residual trapping, which is one type of trapping, and it's shown to occur in a number of different mechanisms. And part of what we do is to develop estimations of trapping and methods to solve the complex problems, to simplify it. And acknowledge my students, and thank you for listening.